Okay, the beautiful joy of rocks. This is where real science kicks in and we get some real analysis of some physical geography. Rocks, of course, are just beautiful. You've got your standing stones there in the Lake District. You've got some people in a little bit of peril there. And of course, humans have been quarrying rock for a long, long time for various different things. But for me, there's nothing better than the ethereal love of rocks, the hexagonal columns of the land of Prometheus, or the land of Iceland. Okay, this is going to be the first of three videos I'm going to make, basically because I tried putting the whole thing together and it's just too long. The first one, we're going to look at the types of rocks. They're igneous, sedimentary, metamorphic, the formation, the characteristics of those. Then the second one looks quickly at the rock cycle and the whole idea of the cycle of rocks. And then finally we look at weathering. But I'm not going to go into too much depth of weathering. I'll do that at a later date. I'm just going to cover what you need to know for kind of a KS4 GCSE level. Physical, chemical, biological weathering. Okay, let's get going. Types of rock. There are three types of rock. You'll know this. The first one we'll start with are the bouncers at the nightclub door of geology, the igneous rocks. We have basalt and the beautiful columnal structure. We have pumice. Wow, that man's strong. No, he's not, because we know that pumice is light. How do we know pumice is light? Because you use it in the bath to get rid of that dead skin off your feet, don't you, children? Rhyolite. Now, when we begin to look at things like rhyolite, we begin to see the grainy structure and the mineral structure of igneous rocks. One of the more famous, of course, is granite. You may see this in your worktop if you've got an expensive worktop, or you might see it in the plastic laminate on your worktop, which mimics. Notice the three colours, the dark, the brown and the translucent. So the translucent quartzite, the feldspar and the mica, and those three minerals make up granite. Some granites are different colours than others, and that's because there are different metals and elements that appear in different places. So for example, you can find green granites out in Italy, and you'll find some beautiful rosy granites elsewhere. Carrying on, we have andesite. Notice here that the grain structure is slightly different, more than three colours, and also the sizes vary considerably. Compare that with diorite. Diorite, not so many different colours, much smaller grain structure, and a penny from America, which is not part of the igneous rock. If we add on my favourite name of rock, tuff. Rhyolitic tuff is the rock that Snowdon is made of, and Snowdon, of course, is one of the strongest things to come out of Wales, apart from Brain Skull Attack beer. Notice again another little coin for scale. We go through peridotite, and here you can see the beautiful green olivine. Olivine is a lovely indicator there may be some wealth in them rocks, because olivine occurs at destructive plate margins, usually with precious metals in their ores, such as gold. Moving on to gabbro, and we're back to the appearance of strange American coins. Must have been a Geological Survey of America site. I whipped this off. Look again, you've got the grain structure, the minerals of quartz, and then the darker minerals that make up the gabbro. After gabbro, we get to the beautiful joy of obsidian, a high silica glass which comes out of volcanic emissions and also can sometimes be found in other places. Those are just a sample of the 700 plus types of igneous rock, each of them a function of the mineral composition of the rock and also how it was pushed out and cooled. So let's break it down to some knowledge. First of all, igneous rocks are formed from the cooling and the solidification of magma or lava. Some of them are intrusive rocks because they were injected into the ground but never broke out to the surface, and some of them are extrusive or volcanic rocks. If something is intruded, of course, then in the cooling process the crystals had time to grow and coalesce, whereas extruded you won't find such large crystals. So if we look back at our diagram previously, which ones are extrusive, which ones are intrusive? It's a game for the whole family. Extrusive, intrusive, extrusive, intrusive. Same slides, same pictures. Can you guess which were intrusive, which were extrusive? Perhaps you should look at the grain structure. Perhaps you should consider how long it would have taken for them to cool down. In fact, what you're going to find out is there is no hard or fast rule about these things. You just got to learn a couple of examples. So how did you do? Perhaps you could pause me, have a discussion. Perhaps if you're on a train by yourself, don't have a discussion. You'll look a little bit strange. So here we go. We have got intrusive rocks: granite, gabbro, diorite, peridot, obsidian and basalt. But obsidian and basalt are actually normally extrusive rocks. There they are in the list there, along with tuff, pumice, of course, with its aeration, andesite and rhyolite. Those are just examples of the 700 rocks that can occur as igneous rocks. Of course, because igneous rocks started off as molten magma, when they have coalesced and solidified, they form very, very strong chemical bonds. So igneous rocks, as I say, are the kind of bouncers at the door of the nightclub of geology. Not much gets through them, or as we'll see, perhaps in hot, wet, tropical environments, they will be weathered in a very, very peculiar way. Next up, sedimentary rocks. Now these are my favourites, and these are my favourites because they've been on that pathway of life. Sedimentary rocks, again, in great variety, but a little less so than the igneous. There are, though, very, very discernible differences. Limestone, the world's favourite rock. Here's a sample with some fossils in it. Next to it, breccia. And you can see here the real beginnings of understanding of what sedimentary rocks are all about. You can see a matrix of very large particles in a kind of it looks from here like a clay dough ball. In fact, if those were chocolate chips and this was cookie dough. Anyway, moving on. So you can see great variety already. Breccia with its obvious big lumps of rock in a matrix of something else. Whereas chert looks like it's actually one solid mineral, and it's the closest sedimentary rocks get really to looking like igneous rocks. Down at the bottom, oil shale. This is the stuff that makes the news all the time. Layers and layers of oil shale rock trapping beneath it petroleum products, gases, oil, and of course all you've got to do is pump down some water, pump down some chemicals, break up the shale, break up those layers that are holding it in, and out pops under pressure your new resource for a new millennium. Go for it, kids. Burn some fossil fuels. Talking of fossil fuels, coal itself, of course, is a sedimentary rock. You just about make out the layers. This is a pencil. It's not part of the coal, all right? Well, of course, there's a bit of carbon in both. Contrast that with sandstone, and sandstone is made up of the very, very fine rock sediments that have been laid down in very, very small amounts. Typically, the grain size of individual parts of sandstone are about 1 millimeter, and 1 millimeter is the standard grading we give to sand. Sands, in fact, are a definition of sediments by their size, not by their makeup at all. So have a quick look at those. Pause me if you want to. Have a big discussion. Here's 3 more, and these 3 I think are quite interesting. Conglomerates. By now we can see lots of rock fragments stuck together, compacted, then cemented. Next to it though, flint. And flints, in fact, are usually found embedded in chalks, and they came from a period of very, very warm oceans. And in fact, each flint, as you can see if you've ever broken flint apart, each flint is a dead sea sponge, or a couple of sea sponges, or a mass of sea sponges. So they're fossilized sea sponges. And finally, mudstone. And mudstone is a good example of how sedimentary rocks get to without quite getting strong enough and cemented enough. In fact, a lot of mudstones with their layers of mud can be broken apart by the hand. Okay, so how do we define our sedimentary rocks? So sedimentary rocks are made from deposits. They can be deposits of igneous material, they can be deposits of metamorphic or old sedimentary rocks, they can be ground down by glaciers, washed down by rivers, but then they lie somewhere building up layer upon layer upon layer, trapping plants, trapping animals. And of course, you're going to get different types of sediments, different abundance of plants and animals, different types of igneous rock would have been weathered in a certain area, and that's what gives us our different flavours of sedimentary rocks, along with how long they've been able to sit there, compacting and then cementing. And cementing is the process whereby calcites or silicates start to actually fill in the pore spaces of these compact particles to actually glue them together. So sedimentary rocks are essentially glued stuff together. If, of course, the pressure of sediments builds and builds and builds, you can get a little bit of recrystallization of some rocks, but that's quite rare. So our subdivisions of sedimentary rocks, as we had intrusive and extrusive igneous, so we have really clastic and non-clastics for sedimentaries. Clastics are purely where we've got broken down bits of rock glued together. So for example, clearly your sandstones are in there, your shales are in there, your mudstone, which we just saw as well, is in there, and your conglomerate with its big sediments. You can always rewind and have a look back at those and see what they share in common. Non-clastic rocks are very different. Here, a very rich water filled with usually calcium carbonate, which has come from, of course, dissolving shells of dead animals in the sea, shellfish, nautili, all of those things. What happens is the water becomes super concentrated in calcium carbonate, and the calcium carbonate comes out of solution to form a cement, and that cement will give you a very, very different texture to the clastic rocks. Examples, of course, are limestone, dolomite, which is limestone plus a bit of magnesium if you're being a bit Jamie Oliver, flints I've mentioned before, your sea sponges, and then things such as rock salts, which we chuck on our roads, which really helps destroy the underside of your car. Well, probably not your car, your mum or dad's car at this moment. And then finally, don't really class it in with the other two, organic. Organic sediments, very, very rich, eventually become coal. Halfway between that, nothing, and coal is peat, and peat is again kind of your mudstone of the organic world. That's sedimentary rocks for you, nice and straightforward. So these are the three processes that give us our sedimentary rock. From deposited sediments, we get first compaction, where layer and layer and layer and layer and layer occurs, and that obviously means that right at the bottom of your column of sediments, you're going to get very, very thin layers because of the tighter compaction. Then a process of cementation occurs, and this, as I said, is when calcium carbonate or silicates fill in the pore spaces and act like a glue to stick the bits together in various different forms. And then finally, you may get some recrystallization of interlocking crystals. They're kind of a little bit like the smell of igneous, this, isn't it? But it's not quite. It's purely due to the cementing and the pressures of sedimentation. Okay, let's move on. Sedimentary rocks are quite important because unlike igneous rocks which flow and cool, sedimentary rocks are layered and layered and layered. So we have two key functions of sedimentary rocks in their structure. The first are horizontal layers formed by weaknesses or changes in climate or the conditions leading to deposition, and they can be seen here. They're known as bedding plains. Check your spelling of plain, please. It's not P-L-I-N. That's where Indians out in the northwestern USA go chasing Wile E. Coyote and all that. Equally, those sediments were once down in the ground and they've now been raised up. They must be because we see them. That means they're under a different pressure environment, and we'll talk about pressure release in the third of the videos. But what we can end up with is vertical cracking, and these are called joints. And the joints, of course, let the water in, and the water can then spread across bedding plains, and that gives rise to some of the most beautiful landscape features you'll ever find. As I say, to me, sedimentary rocks, especially limestone, they are the cool, good-looking boys and girls in the nightclub dancing in some kind of way I can barely remember, that compared to the big macho guys in the door that are the igneous rocks. Finally, metamorphic rocks. Metamorphic rocks, as the diagram shows, are rocks that have been superheated, either from direct contact with rising magma or from the heat down below in the depths of the earth, or because of pressure and folding and melting. But whatever's happened, the sediments have undergone change, and that change takes them closer to being or structurally like our igneous rocks. So here's a few types of metamorphic rock. There's phyllite. Notice you can pick out some layering in phyllite. Schist. And if you look closely at schist, I'll Google it as well to find some better pictures, you can see some glinting of minerals in here, demonstrating that we've had some kind of metamorphosis, some change. Those glints, by the way, and those surfaces that catch light are known in geological circles as facies. Facies. Oh, look, that's nice. Layers upon layers upon layers upon layers cooked together, and you can begin to see kind of quartzite. So this would I'd imagine came from an area where you'd have had a lot of runoff, rivers or ice getting together to give you a large amount of quartz, which has been able to, under pressure, to coagulate and then crystallize out to give you gneiss. Quartzite goes even further, and if you look at the structure of the quartzite, it looks very, very close to being monocrystalline. You've got some differences and some breaks and things and some irregularities, and here you've got a rock that's been cooked up really, really very, very hot. The quartz has been able to dominate, it's been able to become quite massive, a very strong rock. Lots of pebbles on big pebbly beaches are made out of quartzite, and they're the kind of things that when you throw them at another pile of rocks because you're bored with doing your beach profiling, they shatter in very angular material and go off all over the place, and they often get you into trouble and get you told off. There we are. Slate, lovely. Now slate, as you can see, has got its clear layers just about visible down this bottom edge here, but we also know that the actual surface of each layer is very strong indeed. So it's retained some weaknesses of old bedding plains, but it's also got the strength coming down through the plate, as we know, to be used and by humans a lot for tiles and roofs and various other things, including an ornamental clock my grandmother used to have. Anyway, back to limestone. If you take limestone and you cook it up, so you've got your frenzied dancers in the nightclub, but by the end of the night, they've actually changed and metamorphosed into something a lot more aggressive. And they're in fact almost a match for the bouncers who are trying to kick them out at closing time. And here we can see marble. And marble is the metamorphic state of limestone. Strong, massive, crystalline, and we know how strong marble is because people have been using it to build for a very, very long time. So metamorphic rocks, here's the knowledge bit. The first part of the rock, the sedimentary rock, or whatever it was, the protolith as we call it, is heated up either by contact or it's heated up under the pressure in a process known as diagenesis. It undergoes change. Now there are two subtypes of metamorphic rocks. There are those that have kept their layers and their bands, they're called foliated, and there are those that don't any longer have their bands and they're called non-foliated. You see, geology is really easy. So, another game for the whole family. Which are foliated, which are non-foliated? Shall I go ting and wait, or shall I pause, or shall I just show you? It's pretty obvious because, of course, it's been done on appearance. And if they've got layers, you can see that they are foliated. Note schist. Although the schist on first appearance doesn't look foliated, you can just about make out some layering. There's a vein, for example, coming through here. Quartzite and marble. Clearly no lines or bedding planes left with those babies. So that's it. That's the first of our videos, types of rock. I hope you'd enjoyed it. See you soon.